Okay, let's do a couple trig identities questions together. The first thing that you need is basically this little slip that I gave you this semester. It's the Fundamental Trig Identities slip. And I gave you guys a couple tips about this slip. One of them is that any of these three Pythagorean identities can actually be arranged. Specifically, we like to take a look at this one. I can either move sine squared x to the other side, or I can also move cos squared x to the other side as well. Okay, so that rearranged identity, the first one would be if I moved the sine squared x to the opposite side. Okay, and that means that cos squared x would stay on the left, but sine squared x ends up being negative. Okay, the second rearranged identity would be if I left the sine squared x where it is on the left side, and I moved the cos squared x. Okay, be aware that these are two identities that we use very, very often, sometimes even more often than the actual Pythagorean identity itself. These two identities we don't use as often, but they still can also be arranged to suit whatever you need. Okay, the other thing that I told you guys was that it's important to know that I can square both sides of either of these identities or any of these three as well. So for instance, I can take tan x and I can square it as long as I square these two sides as well. Okay, same with cotangent, so I can do cotangent squared x, and as long as I square cos x and sine x, that can still hold true. Okay, same idea with the Pythagorean identities, reciprocal identities. If I square cosecant x, I can also square 1, which is just 1, and sine, and that identity is still true. Okay, same with secant and cotangent. Okay, we also use these identities fairly often as well. Okay, those are kind of the main things that you need to know with rearranging the slip. So those kind of things are important. Okay, there's also some tips that I talked about that are fairly important in this in solving trig identities. First tip, try to get everything in terms of sine and cosine. Okay, when we do that, we basically get everything in terms of the same two things, or the same couple things, so that way we can see what can be canceled and what can be gathered and things like that. If you have a bunch of different trig identities, you're never going to be able to see what can be canceled and what can be changed. So our goal is to try to get everything in terms of sine and cosine. Second tip would be to try and work with the more complicated side first, okay? See if you can simplify that more complicated side a little bit. Sometimes what I do is I will simplify the simpler side as much as I can by getting it into terms of sine and cosine, like the first step says. And then I'll start working with the more complicated side to see if I can make it look like the simpler side. Okay, the next step is to use foiling and factoring. Specifically, we use difference of squares a lot. So for instance, if I have something like 1 minus sine squared x, this is actually a difference of squares. This factors into two of the same brackets, one with a plus and one with a minus. And remember, to factor difference of squares, we do the square root of the first, which is 1, and the square root of the second, which is sine x. Okay, so we use that quite a lot. We can also do the opposite of that, and that is that, so this would be factoring. We can also FOIL. If I have something like sine x plus cos x times sine x minus cos x, okay, I can go ahead and actually FOIL this thing out. So we'll do sine times sine, which is sine squared x, sine times cosine, cosine times sine, and I'm running out of room here, and then we'll get negative cos squared x, and these actually end up canceling out. Okay, this guy and this guy is the same, so I end up with sine x minus cos x. Okay, and the last step is that if you're adding and subtracting fractions, you should find a common denominator and merge them into one. Usually this will be very effective, so try to do that and then see if you can FOIL out the top and simplify it all. Okay, enough of the tips. Let's try an actual question together. The way that we set up a proof is we're essentially going to separate our left side and our right side. And I'm going to make sure that I don't cross this center line right here. This center line basically tells me I have to work with the left side and the right side completely separately to try and get them equal to one another. Okay, there's a couple ways that we can do this proof, a couple things that we might be able to use from our tips and from our trig identities. One of the things that I think might be helpful is this identity right here. Cotangent equals 1 over tan x. Now I know that I told you my very main first thing was to get everything in terms of sine and cosine. That is true, but in this case, I think this one is a little bit of the exception here. Because I know that cotangent is equal to 1 over tan from my list of trig identities, I can actually go and plug in 1 over tan theta here. Okay, and I'm just going to multiply this tan squared theta inside the brackets here. So we have tan squared theta over tan theta. And one of these from each thing here cancels out. So I'm actually just left with a tan theta. Okay, and then we're going to say left side equals right side and do our little bragging box to say that we're the greatest mathematician, and we finish the proof. Okay, here's our next example. Prove that secant squared theta plus cosecant squared theta is equal to secant squared theta times cosecant squared theta. Okay, so let's set up our proof again. Left side and there we go. Okay, left side and right side. So I'm just going to recopy my left side, secant squared theta plus cosecant squared theta. And secant squared theta times cosecant squared theta. Okay, so, and I just realized that I wrote this wrong. Cosecant. There we go. Okay, couple things that we might do here. Let's look back at our trig. Here's two identities for secant and cosecant squared. They're not really going to help us because we get them into the terms of tan and cotangent, and we don't have either of those on the left-hand side or the right-hand side. So I'm going to suggest that we maybe use the first tip that I gave you, and that is to turn everything in terms of sine and cosine, and then hopefully we can figure out some kind of common thing that we can use here. Okay, so secant is the reciprocal of cosine. And I'm going to use these rearranged identities from the front that we talked about. Okay, so we have 1 over cos squared theta and 1 over sine squared theta. And I'm going to do the same thing on the right-hand side as well. So I'm going to have 1 over cos squared theta times 1 over sine squared theta. Okay, and I'm just going to merge these into one. We'll have cos squared theta times sine squared theta. At this point, I'm not too sure that there's much else that we can do with the right-hand side, so I'm going to continue with my left-hand side here. And one of the tips that I told you earlier was if you have two fractions being added or subtracted, try and find a common denominator. So I'm going to give this side a cos squared theta, and I'm going to give the left-hand side of this a sine squared theta on the top and on the bottom. Okay, so I'm going to merge these two fractions. I'm going to have sine squared theta plus cos squared theta over sine squared theta, cos squared theta. Okay, so I know what you're thinking right now. You're thinking, oh, I'm just going to do this and cancel out everything. You don't want to do that. When you have a plus on the top, you're not allowed to cancel separate pieces, separate terms of that expression. What we do know, though, is that sine squared theta plus cos squared theta, looking back, is equal to 1. Perfect. So this is equal to 1. I'm going to plug in that identity, and it's 1 over sine squared theta times cos squared theta. And is that the same thing as this? Is 7 times 9 the same as 9 times 7? Yes, it is. So we can now say that left side equals right side, and we're done our proof. Perfect. So that's just a couple examples of trig identities. I hope this is helpful to you, and Yeah, that's it.